So hey, Steve, amazing to see you. I don't think I've seen you since the King's Honours came out in the new year, so massive congratulations on the OBE. I can see I'm making you blush, but it's an incredibly well-deserved achievement on top of being already founder and CEO of Riverlane.
Thank you. It was a bit of a surprise, a really nice one. I think kind of a big testament to everything that the team at Riverlane have been doing. We've made a lot of progress in quantum computing recently, and I think it's started to capture people's imagination, and it's really cool.
Incredible. So, I already know Riverlane's in quantum computing, but where do you actually fit in that space?
So we solve the error correction problem. So to build a quantum computer, there are lots of different types of qubits. We don't yet know what's the equivalent transistor of quantum computing. So people are exploring different qubit types, and there are lots of great companies and research labs doing that. And we sit on top of the qubits to correct errors during the computation. And the reason that's needed is that qubits are extremely fragile. So the best quantum computers in the world, they can currently do around 100 operations before the noise in the system just starts to take over, and then the computation effectively becomes just random noise, and that it sort of stops, right? Like, to do something useful with a quantum computer, we need to get to millions and trillions of operations. And so that gap is bridged by adding active error correction. I think a good analogy that I like to use is in your SSD card. So that's built out of faulty components, so error-prone components, and then there's this active layer of error correction running all the time that's moving data around, so that the user of the system just sees read-write instructions. The computer doesn't really care what's happening underneath. So the same kind of thing is what we're building in quantum computing. So on top of the qubits, we apply our stack. We do this with lots of different companies, it's kind of that's the central problem that we're trying to solve.
Okay, amazing. It certainly sounds like a very Cambridge problem to solve. So, we're sitting here in Selwyn Bar in one of the colleges, and just you can almost feel the technology history that's in the area. I see that quantum computing is not quite there yet, but once you have solved the kind of error correction and scaling problems, what sort of areas do you think are going to benefit most from quantum computing?
So for me, the biggest applications of quantum computing are the simulation of physics. And just to kind of break that down a bit, so we want to be able to simulate the world in order to design new products or new medicines in many different industries. And that happens very effectively in areas where you can currently solve the equations of motion, right? So you have a model of the world, like a law of physics, like the Navier-Stokes equation and so on. And then we have computers today that can solve those equations. And so in those areas, we can already use computers to design products. But when we try to simulate the world of atoms and electrons, of proteins and their interactions, of chemistry, of material sciences, the law of physics at that level, at the microscopic level, is quantum mechanics. And classical computers are really bad at solving quantum mechanical equations, or at least we have to make approximations in order to solve these problems. So with a classical computer, you add one more electron, add one more atom, you need to double the size of your computer, or you need to make some approximation that sort of rules out some of the physics. Whereas with a quantum computer, we could now solve those equations of motion. So add one more atom, it's just adding one more quantum bit. And so the scaling in quantum computing means that we'll be able to simulate for the first time accurately how proteins move, how they interact with organic molecules in drug discovery, or how electricity moves across a material, or how a catalyst lowers the energy consumption in some chemical process. So it's a really kind of foundational type computational capability that is currently impossible, and I think would would never be solved without building a quantum computer.
I see. So those those are the kind of problems that actually, it's not just about accelerating compute, it's about solving problems that we actually can't do today.
Yes.
And that sits very closely to a lot of the things that we already do at Altair in terms of physics simulation and things like that. So I think from my point of view and from Altair's point of view, it's going to be incredibly exciting to see when that starts to become practical. So I know in the past you've talked to me a bit about a sort of a Moore's law for quantum computing. I think we're all very familiar with Moore's law for silicon, but is there a Moore's law for quantum computing, and can we use it to predict when quantum computing is going to be practical?
Yes, there is. So back in 2006, I was giving a talk at a conference explaining a new quantum algorithm, so an algorithm that would run on this quantum computer. And at this conference, there was this kind of straw poll where people were saying, oh, hey, when do you think there would be a quantum computer? And about a third of the community said at that point there would never be a useful quantum computer. And I was a bit shocked at that point, like I'd kind of been working on these algorithms and maybe it was a complete dead-end research area that would just never be used. And so I got talking to the experimental physicists, so the people building quantum computers at that point in time. So started asking, essentially, like, how good are you at building a quantum computer today? And the metric for that is kind of the hardest bit of building a quantum computer are the 2-qubit gates. So this is the entangling operation. So you have 2 quantum bits, and if you could do an operation between them, that's kind of the hard thing in quantum computing. So you can measure how good we are at doing that. And that's a really good measure of kind of progress in the field, at least in the kind of smallest, early stages. So I started asking everyone, like, how good are your 2-qubit gates, basically, across different qubit types. So there were people who were developing quantum computers based on atoms, or based on superconductivity, or based on photons. And kind of how good are you today, and how good were you last year and the year before, and started to plot the progress in the field. And that's where I saw this kind of Moore's law already at that point. So in 2016, there'd been kind of 15 years of progress in quantum computing. And we saw a sort of doubling in fidelity, so how good you are at doing 2-qubit gates, every 12 to 18 months, and that this was common across the 4 or 5 different approaches for building a quantum computer. So that trend has continued. So we've now had 2 decades of a sort of quantum Moore's law. And so we're now at the point where the quality of the 2-qubit gates of the components of a quantum computer is sufficiently good that you can add error correction to then massively boost the capability of the quantum computer. So this is a super exciting, 2023 was a really exciting year because we sort of got to this point, and so you started to see a bunch of experiments demonstrating for the first time that error correction, some of the basics of error correction. And so the next 3 years, I think, is going to be amazing for the field. The goal is to get to the first quantum computer that can do 1 million quantum operations without a single fault. Right? And so we're going to go from 100 to 1 million in about 3 years. And that's because we can add this error correction on top and leverage all of the development that's happened already.
Amazing. So that's going to make a huge difference. That sounds better than the silicon Moore's law. So it does certainly sound like quantum computing is becoming more practical. Are we all going to have to retrain to be quantum computing experts? Should I be doing a physics degree on the side, or do you think there's still going to be a need for high performance computing kind of alongside quantum?
Yeah, well, physics is really cool, so anybody should learn about physics, but absolutely we need other skills, and lots of them, and I think computing is an area where we can learn a lot about what's going to be needed. And I would say one of the exciting things that's been happening within quantum computing is people with other skills have come into the industry and brought knowledge of how to solve similar problems in other areas. At Riverlane, we have embedded software engineers, we have chip designers, we have people who understand real-time processing. These are all skills that come from other industries, and we're now applying to the kind of central problems in quantum. But in terms of actually using the technology, we need to bring it to people. So I think HPC is the perfect analogy here, because HPC is a community where you have different types of compute. Like, you've gone through that journey of having just a CPU to having GPUs and CPUs and other types of compute. So a quantum computer is going to be another type of compute. So it will be a QPU that you add into the mix. We're definitely going to continue to need HPC and these other types of compute. So quantum computers are not going to be used to send emails, or there's a bunch of problems that will still be run on the CPU, bunch on the GPU. It's just there's a very particular set of problems that quantum computers are really good at. So you could imagine in this simulation of a protein, you map some of that simulation problem onto the QPU, the bit that's got these kind of strange quantum effects, like perhaps it's part of the metal atoms in that system. So that's somewhere where we know there are weird quantum correlations. So put that on the QPU, and then the rest of the simulation that is well approximated by classical physics, that can then run on the GPU or CPU. So it's definitely, I see this as a mix of compute types, and so we need to figure out how to pull all this together.
Okay, well that's certainly reassuring from from my point of view. And last year, I understand you brought out the first error correction chip. So yeah, what kind of a difference is that going to make?
Yeah, no, last year was a great year for us. So we launched the first ever decoder chip. So this is the chip that solves error correction. It's a bit like the GPU equivalent in quantum computing. So in order to solve error correction in real time, we need a very fast processor. And what that processor is doing is taking the data that comes out of the quantum computer, analyzing it, and then making a decision about where the error occurred. And that needs to happen very quickly. So it needs to happen at a rate of megahertz, because that's essentially the clock cycle of the quantum computer. So the only way to solve that is to build a dedicated chip. And we launched the first generation of our decoder chip last year, and we've been working with companies building qubits over the past year or so to integrate that into their system.
And I mean, presumably everyone with a quantum computer is going to need this error correction capability. So who are your partners and customers?
So we work with many of the world's leading hardware companies, so companies like Rigetti, companies like Inflection, who are building different types of qubit. The decoders that our team developed have been used in experiments at Google, at IBM. The whole ecosystem is really alive right now. So we work with sort of anybody who wants to do something exciting on error correction.
All right, sounds good. Well, here's to amazing 2024.
Yeah, thank you.
Cheers.
Cheers.